Hello, hello. Okay, I think we're going to get started this morning. We have presentations from some very, very special researchers from the National Research Council, and today we're going to start our day here at Cool Science with the Centennial Science Show, which is my name for our lecture series, because I think we're putting on display some of our wonderful researchers and some of the great research that we've done here at the National Research Council. My name is Bianca Petours, and I'm your Master of Ceremonies for the day, and I'll tell you a little bit about what was behind.
Oh, that's the introduction.
I'm going to tell you a little bit about what motivated me to set up this series. Is that when I started working at the National Research Council, and I'm in human resources, and I'm on the hiring services team, and I drive over to the Montreal Road campus, and every day I was just absolutely smitten with this employer of mine. I was always discovering new people, and I was always discovering what people were doing in research, and every day I went, wow, what an amazing place. And I realized that from the inside and from hiring, we were really lucky, because we'd be peeking into all these different portfolios and really getting a sense of what was going on there. And I thought, well, the whole world should discover this and should have an opportunity to find out a little bit more about the council. And it's our research council in Canada, and it belongs to all Canadians. So that was my motivation, and my counterpart, Elena Tilno, who's here from communications, started me off, and she told me about Paul Corkum, and she told me about some other people, and I had the good fortune of running into some of the other people that are going to be presenting throughout the day. But I thought the NRC is so cool. What could be more perfect for Cool Science than to put some of our researchers on display and let you discover them too. So we're starting our morning with the history of the laser in Canada, and lucky us, because we have one of the researchers that was there and that built this first laser, which is sitting on the table next to me. And so Alex Szabo, Dr. Alex Szabo was one of the researchers with Dr. Boris Stoichev, who developed this laser in January 1961, so it's 55 years ago now. And he has a PhD in laser physics that he got from Tohoku University in Japan, and has been working in photonics, which is what is the official name for laser science, and was also built an optical maser before he built the laser. So I would ask you to give really a warm welcome to Dr. Alex Szabo, and I'm going to turn it over to him.
Thank you for that introduction. And good morning, everybody. And thank you for coming, braving the weather out there. Also, thanks to the organizer, in particular, Bianca Petours. So today I'd like to recount how the first laser was created in Canada. The time is January 12th, 1961, about 6 months after Maynard's first demonstration of laser action at Hughes Lab in USA. The place is the spectroscopy lab at the NRC on Sussex Drive. Present, besides Dr. Boris Stoichev and myself, were the lab scientists and 2 Nobel Prize winners, Dr. Hertzberg of NRC and Dr. Szabo of Bell Labs, who was visiting at the time. I had transported the laser power supply and laser head here, which I had just completed at my lab on Montreal Road. And also Boris and I had each just received laser rods from our optical shop, and thought this would be a good occasion to test things out. So the ruby rod was mounted in the laser head here, and this is in the first slide. Get that up. Okay. So it essentially consists of a brass can inside of which is mounted a spiral flashlight. And the rod is mounted along the axis of the lamp. The rod is silvered on one end and partially on the other to let the laser light out. And more details on how the laser works will be given by Dr. Corkum. So after several flashes without success, trying my rod, we next tried Boris's ruby rod, and again, no success. The problem was that the strain in the rods distorted the wave inside that's bouncing back and forth between the mirrors. And if the distortion loss is greater than the gain, then you don't get oscillation or laser action. So at this point, of course, things look pretty gloomy. Dr. Szabo, with a smile, reached into his pocket and pulled out a ruby rod and said, "Try this." And it produced a laser beam on the first shot. And the thing about this ruby is that it was from a company that was developing low-strain rubies. This was the secret as to why the thing worked. So to the layman on the street, this demonstration would probably not be impressive. It would be just a red flash of light on the wall. But to scientists, this was something awesome, because now for the first time we are seeing coherent light. And what this means is light of a single frequency and highly collimated. In audio terms, this is like the difference between the pure note and noise. The collimation property means that the beam can be focused to a very small spot, so that this allows the development of things like DVDs, CDs, and optical fiber transmission, which makes possible the internet. All of these things need a laser. And there are, of course, now many other applications in medicine, material processing, welding and cutting. So we're way past the point of looking for problems. I might note here, paradoxically, the laser has also been used to cool materials to about 200 degrees below zero. And if someone asks, I can go into this in more detail. Now, an interesting question is, why did it take some 50 years from Einstein's discovery of stimulated emission to finally construct the laser in 1960? And I can think of two reasons anyway. One of them is that in the early days, theorists sort of sat in one camp, and the technologists really didn't understand what the theorists were doing. Now, I'm sure there are many other reasons as well, but those are certainly two of them. So, a popular cynical comment in the first few years of the laser era was that the laser was a solution looking for a problem. We all remember that one.
Yeah.
So, my research made use of the single frequency property of the laser. And in my lab, we were the first in the world to show that how lasers can improve the resolution of spectra in solids by up to a factor of a billion. And there's one possible application. I propose to use this effect for a new kind of computer memory, which writes information with different colors, and received the US patent in 1965. Practically, this means the possibility of storing 1 million DVDs on one DVD. So IBM patents followed in 1967 using different materials, however using the same principle. So far, the idea is still in the lab, and the main reason for this is that it needs cryogenic temperatures whereas lattice vibrations at room temperatures destroy the hole. The same kind of problem exists in the search for room temperature superconductor. However, very recently, theorists have indicated that it may be possible to construct materials in which the lattice thermal vibrations, or in the scientific parlance, the phonon modes, don't couple to the memory pattern. And I eagerly await further developments in this area. Recent work is also underway to try to achieve the current holy grail of a quantum computer using our techniques for solid-state crystals, among many other approaches. The next slide. Let's see. Okay, this shows a page from my lab book, turning brown, as you can see, after some 55 years. On the top of the page, dated January 12, 1961, it reads, "Successful laser action achieved using an R cell and flashlight and ruby rod borrowed from Szabo of Bell Labs." And as shown in the later notation in my lab book, on January 24th, I finally got my ruby to lattice. However, I had to cool it to liquid nitrogen temperatures. And this was necessary because this results in higher gain in the ruby, which then can overcome the losses due to distortion. And that's the end of my story as to how the laser was first done in Canada. And now that I have this soapbox, I would like to make a few personal comments and aim perhaps mostly at the younger people in the audience. I see a few here. I'm often asked at social gathering, what makes you run? And the answer is one word, one that means you'll never be bored, and that word is curiosity, which incidentally is the name of the latest Mars rover. I gave a similar talk like this 5 years ago, and a few months after that, the Mars rover appeared with the name Curiosity, and I said, "Isn't that curious?" So another question I get is, by now there can't be much new physics to discover, so where's all the excitement? A similar remark was made by Lord Kelvin in the late 1800s, to his regret, I suppose. The effect that physics was done, and all that was left is a few loose ends to clear up. Well, in the early 1900s came Einstein's relativity theory, which, for example, gives us GPS in our cars. Then this was followed by the quantum theory, which gives us lasers, semiconductor technology, responsible for all the electronic marvels of today, and many other advances. So a major problem with the quantum theory is that it's essentially a black box with a handle we turn, which correctly predicts every experiment ever done. After 100 years, the best minds have yet to make sense of what's inside the box. All we know is that it works. And there are at least a dozen interpretations of what might be going on, but nobody agreed. And the popular one changes from year to year, and currently it's the Everett interpretation, in which he says that every possibility that can occur, but it occurs in multiple universes. Well, that's kind of hard to swallow, but if you want to believe that the quantum theory is complete, it's the only logical answer. And I remember when I was at university, the profs there, this was a popular interpretation. This kind of varied over the years, and then over the last, they got away from this, but in the last couple of years, they've come back to that with variations. So it's, as you can see, it's a bit of a mess as far as trying to understand what's going on. But the important thing is that it works. You know, many people don't know what makes a car go, but they can drive it, fortunately. So, the world at the atomic level is different from our everyday, where objects have a specific place and velocity. At the atomic level, objects, if indeed they can be called objects, can exist in several places at once. So another weird prediction of the theory is that two prepared objects, let's say spins or photons, can be separated by a large distance, up to 100 kilometers has been actually done. And they apparently can communicate at speeds faster than 10,000 times the speed of light, or essentially instantaneously, if you take into account errors. I say apparently because a minority, including me, argued that there are loopholes to consider, but these are slowly being closed. Some people claim they have closed all the loopholes, but then papers come up, oh, you didn't think about this possibility. So the experimentation and the theorists are still batting back and forth at each other. Einstein was the first to point out this weird aspect of the theory in 1935. But it took people 20 years to actually do an experiment to see if this prediction was true. And he referred to it as spooky action at a distance. And his belief that the quantum theory was incomplete. It is this property called entanglement, which is being exploited in the race to build a quantum computer, which, if it's successful, would be enormously faster than a regular computer. So I leave you with these few observations, hoping that they've aroused your curiosity. Thank you.
Thank you very much. I'm wondering if anyone has any questions in the room. I know that...
Can we leave them for the end?
Yes, we can leave them for the end. Absolutely.
And,
absolutely.
Let Paul get his talk, and then we can face the audience.
Absolutely, we can do that.
Okay.
Thank you very much for sharing with us this morning. I'm going to introduce our second presenter, and I'll start by saying that the first time that I went to meet him in his office, I sat in...
I am not a true expert on Michael.
What is being detected is the actual change in length of one or the other arm. And this change occurs because of the deformation of space by the gravity wave. They have recently increased the sensitivity of this machine, and they can now detect changes in the length. Each arm is a couple of miles long, but they can detect changes of 10 to the minus 18 centimeters. And
So do you want
compare that to
Does it-
the size of an atom,
Yeah, do you want to?
which is
Okay, just
which
one
is
second.
10 to the minus 9 or 8
Minus
seconds.
eight.
So it's, you know, that fraction of an atom that they can detect. They use laser beams currently now about 300 watts. And as Paul said, when the two beams come together again, they adjust the phase so that they interfere and they cancel. So that essentially they're looking at a zero background. And if the arm length changes because of the gravity wave, then you'll see the light coming through. And I just read this on the web the other day. I'm amazed at the sensitivity of this thing, 10 to the minus 18 centimeters.
I didn't know the 10 to the minus 18. That's very good. That's amazing. So an atom is at 10 to the minus 8 centimeters. So less than a billionth of the dimension of the atom. That would be less than a billion. It's amazing.
Do we have any other questions here in the room? Yes, absolutely.
Yep,
So, full disclosure, I've known both these gentlemen for a long time. It's not totally a setup question, though. I've known Alex, since the mid-'70s when I was a student. Yeah, it's okay.
Yeah, you're
I'm
good.
loud enough.
You're good.
And I worked in his lab. My question is this: how many students do you two gentlemen think you've had that's encouraged them to go on into science like me?
A couple of dozen anyway. Yeah, it's always a nice thing to have students because they bring a certain, well, naivety but also energy, and they question everything that you try to ram down their throats, and it makes you a better person, I think. So
I will make a comment in the opposite sense. From the student's point of view, they question everything we do when they ask us why we did it wrong.
You're not the only one that does things wrong.
Let me thank you.
Okay.
Well, when I met with Alex, I asked him, and it's Dr. Szabo, but when I met with you, I asked you, what are the 3 qualities that you think are important in a scientist? We've got lots of young people here today, and I'm sure there's a lot of people that are interested in science. I know at our house, I have the coolest job because I come home with a story frequently. So what are those 3 qualities that you think we need in a research?
I mentioned one, of course, curiosity. And at my museum talk 5 years ago, one guy asked, so, how do you get curiosity? And the only answer I could give at that time was, I guess you're born with it, but you can also take positive steps, I think. Just don't accept everything you see. And try to get beyond the on button. Maybe ask a question, well, what's going on? How does it work? But I guess there's so many new gadgets these days that it's maybe hard to keep up. You're just content to hit the on button. Okay, there's nobody going to ask me about how you can use lasers to cool things? Okay.
Now, when you said about 3 things for scientists, if I was you have to have patience, I would think, because if your first thing doesn't work, you have to have patience to keep trying.
Yeah, that's a very astute observation. Usually in doing basic science, things never work. You have to keep trying. But there's the odd time, and I've had this, where you lash together an experiment and it works. You say, okay, well, this was a lash up, now I'll do it properly. So you do it properly and it doesn't work.
I've had that experience too. Actually, maybe I can interject here, because there's a very unusual aspect of science that almost nobody thinks about it. It's not so much unusual in the rest of the world. So I think people see scientists as people who go into the laboratory. They can't really get along with people. They sort of work in their thing all by themselves. And, it's kind of an isolated profession. And that is really not true. I don't know what your experience is. In the end, almost every science paper is written by a set of people. In this case, Boris and Alex wrote the guest paper on some lasers, and I think everything is done in groups. And so the subject is quite, quite social, really. You give talks all the time, as we're doing here, and you travel and you have colleagues around the world, and you get to know people all around the world. And so the perception of scientists is these sort of asocial people who go into a room and can't really speak to anyone else. It's just not correct. So I just thought maybe that's a perspective you might not think of.
About getting to know people, well, that's very true. It was mentioned that I got my PhD in Japan, and the way this happened was that I met this professor, head professor, at several conferences, and we were doing very similar work. So whenever we were at the conference, we'd get together and talk it up. And I didn't have my PhD at that time, and he says, well, come to my lab and give it a go. This is what I did. So I was off to Japan for 4 months to defend my thesis, and that's how I got my degree. But as Paul says, there's a lot of intermingling that goes on. People tossing ideas back and forth. This is an important part of science that you just don't, except for maybe people like Einstein who can sit in a room and develop the whole of science. But usually we work in groups and toss ideas back and forth. Yes?
Does your laser still work?
It probably does.
You don't have the power supply now?
I don't have the power supply. That's long consigned to the junk heap. But yes, it would certainly work.
Speaking of that, what would be the power output of that
Power
particular
power output is the peak power would be several thousand watts. The total energy would be maybe one joule. Remember that 1 joule per second equals what horsepower?
I don't know what a horsepower is. I know what it is, but I don't remember.
1 watt. 1 joule per second is 1 watt.
Okay, that I know.
Yeah.
I thought you were going to.
Still have a super. So it doesn't work continuously. It works in a pulse fashion. Although later on, people did make the ruby laser work continuously, but it almost melted. So that wasn't a popular way to run the thing.
So
There were many other kinds of lasers then invented which work continuously.
I was going to say the trick is to get the population up before it can leak out of the bucket. You remember the thing? So flash lamp going fast and moving it as fast as you can. It's the best way, and it's the first one ever. And if you look at it, you'll find that the flash lamp isn't just a line or something like that, something simple. It's one right around the rod, so it just as close as possible, so you get as much light. And it's like pouring the water into the bucket as fast as you can. This is the fastest thing with it.
Actually, a later version of a laser, I had instead of a spiral lamp, I had straight lamps, and the box was 4 ellipses, partial ellipses, of the lamps in focus.
So everything came to the lamp. The whole idea is to get the light into the lamp as fast as
That's however you
or into the rod.
Yeah.
Into the rod as
But these days, the lamps are pretty well going out of style, and they now use diode lasers as pumps. And the thing that's nice about the diode laser, it's one frequency, so what you can do is specifically excite the energy level that is going to give you laser action, as opposed to a flash lamp, which puts out all wavelengths, most of which you don't use.
I'll ask the question that you wanted us to ask about how do you use lasers for cooling?
How do you use I was asked this question by a lady at the museum talk I gave, and she was mystified. She says, I thought lasers could, all they did was heat things. You know, that they burned through metal, and even these days, which I might come to later, the military is starting to use them to shoot down things like drones, but they haven't got to the bigger things, but they say it's on the way. Yeah, so she said, how is it possible that it's cool? I say, well, what you do is start with a piece of very pure glass. And you can shine your laser at it, and it won't heat up because there's no absorption. The light just goes through. So the next thing you do is you dope the glass with a rare earth ion, which has specific energy levels. And for example, you can shoot a red laser beam which is resonant with one of the energy levels, and you observe that coming back out is blue light. Now blue light has a higher energy, or the quantum of blue light has a higher energy than the quantum of red light. So the solid is losing energy. So it's got to cool. So now the question is, how come you get blue light out and you put red light in? And the answer is that the lattice vibrations excite the atom from the red level up to the blue level. Now, in the scientific parlance, a phonon is absorbed. And when a phonon is absorbed, you're essentially extracting thermal energy from the solid, so the solid cools. And this kind of technique has been being further modified. For example, they now put the solid inside of a cavity. In the case where you just shoot the light through the solid once, you've lost it, it's gone. So we put a mirror here, you reflect the thing back through the solid, and you have a mirror here, so that the light is just like a laser. It's bouncing back and forth, and you can amplify the intensity of the light by 1,000,000 times. So the intensity of the light inside the cavity can be 1,000,000 times higher than it is outside. This is also true, incidentally, of the interferometer. The interferometer power inside is up megawatts. That's why they have to keep the arms in the vacuum. So using this technique, the initial attempts were sort of 20, 30 degrees, but they've been slowly improving this by making the glass or the background material purer and purer so it doesn't absorb, and also using tricks on this, putting the sample in a cavity. So they've gotten close to liquid nitrogen temperatures. And the thing that stops you eventually, of course, is that there's fewer phonons or vibrations that will excite things up to the blue. And also there's also residual absorption, which eventually stops you from going further down the temperature, but they're still working on this. I'm sure they'll get down to even lower temperatures. Yes?
There's a question from one of the...
Yeah, there's a question up there.
significant do you think the discovery of quantum computers would be, and could they be used in everyday life like lasers are?
No way. There's all kinds of approaches, some involving light alone. The most popular one seems to be trapped ions, and actually building a semiconductor kind of trap. So you have a semiconductor in which you have atoms being held in traps. And I read something the other day that thought maybe this is the best approach, but then again it was written by someone who was actually working on that. So there are all kinds of other approaches, but say for example, to use solids with some of the techniques that I mentioned that I was working on. Your solids have to be at liquid helium temperatures. You're not going to have a liquid helium temperature computer sitting on your desk. So but even to get one working there, it's still far from being realized. And in fact, there have been several papers by people pointing out that, or claiming, and backing it up with, I thought, reasonable numbers, that in fact it would never be realized. Of course, never is a very strong word, and some people react to that kind of thing. But it means essentially that, let's say you need 100 qubits in your computer. Qubits are the quantum equivalent of the regular bit that you have in a computer, 1 and 0. The qubit, its advantage, it can exist anywhere between 1 and 0 in a so-called superposition state. And the quantum computer works by essentially running in parallel. It's a massively parallel machine. Now, but in order for this to work, these atoms have to be completely isolated from the world. They can't, there can't be any thermal effects. There's all kinds of things that can upset the entanglement. It's the entanglement between these bits that does the computing. And any kind of jostle can spoil. You have to maintain phases between all these 100 bits. And any kind of interruption completely ruins the calculation. And for this reason, several people have claimed that it will be impossible. So, that's the situation. Yes? Excuse me?
The most common uses for your laser.
I think we've got another part of the presentation that might answer that question.
I'll let Paul take care of that.
I'm not sure I can answer it. If you ask the ruby laser, it is no longer used very much,
No.
I would say.
No.
So there was the first laser, as I said when I was talking, there were, within a year or two, 100 everywhere.
Yeah. Another use I would mention is my wife has cataracts, and what happens with cataracts, the inside of the lens gets smudged up. And what they do now is they use a laser to blast away the smudge. And I actually witnessed this going on. And it takes about 5 minutes. And the doctor said that before the laser, this was a very delicate operation that took a couple of hours. And now they could do it in 5 minutes. And I could look through the microscope and I could see where the smudge was on the inside of the lens of her eye. And then after a few blasts of the laser, this was gone. So there's one use. It's not the most popular use, but
But lasers are entering the manufacturing industry to try
Oh, yeah.
just to make sure things are more accurate, so your car runs longer, right? Everything is done better, and it's because they're so precise. I guess your cell phone glasses come with lasers, every glass. So I was just trying to think of a few things. So everywhere you look, there are lasers.
You used it this morning with the pointer.
I used it with the pointer. Actually, maybe I can interject on the last point about quantum computing. I heard a presentation by a man from Lockheed, his name is Ned Allen. And Lockheed has said they'll spend research money in Canada only in quantum computing. So this, and they probably wish to solve, I'll tell you, because you asked what problems could be solved.
Other uses for it in solids is you have things in orbit and you want to cool them. So you can use a laser which is being excited by the sun, let's say, and this is good one. And then the laser cools your solid. You want to keep your detectors, say, at a low temperature. Another use that I recently saw was that in semiconductor circuits, you might want to cool just one little part. And the thing with the laser, of course, is you can shine it to a very small spot. And if you just want to cool one part of your circuit, you can do that. And the cooling materials have actually been extended to semiconductors as well. So you can shine light into a semiconductor and it will cool down. So this is now where things are being developed, and I think we'll see some applications here.
It's quiet. I don't know if it's helpful or not. Anybody be interested? I have a presentation made by 7 students. I gave a talk at a high school class about 5 years ago. There were 2 students in my group, and I said, why don't we, 3 of us go? And you tell the students, high school students, what it's like to work in a science lab. So it's their presentation, it isn't mine, it's not very long. I can tell you what happened to both of these students, but maybe I'll do it as it goes along, if anybody's interested in seeing. So I didn't know if students would come or not, and I just brought it along, and I haven't changed it at all. It is their presentation, but I'll say a few words with it. Would you like to see it? It's got 7 or 8 slides. So it's completely different to what we're doing, and probably that would take us full time, and then we'll...
And we do see on